Our next topic is universal gravitation, and it still is in with circular motion. I'm going to introduce universal gravitation with a lab that measures the intensity of the light at various distances. And you think, well, how does that relate to universal gravitation? Well, let me describe my apparatus here first. If I had this little gray tube here as a light meter, and it's going to plug into the computer and it's going to measure the intensity of the light every 2/100ths of a second. You can imagine if that sensor were really close to that light bulb, it's going to be very intense. It's going to measure a high intensity. And the further and further away it gets, the weaker and weaker the intensity. Well, I'm doing this because light behaves very similarly to gravity, in that the farther away light you get from the light source, the weaker the intensity, and the further and further you get away from the gravity source, the weaker and weaker the gravity. So they do follow very similar relationships here. And so there's two things I want to accomplish in this lab. One is to find the mathematical equation that relates distance and intensity, but then I also want to introduce a new technique of dealing with errors in our data. So the first thing is to find the equation. It might be a linear relationship. It might be that we take the distance we are from the light source, multiply by a number, add a number, and that could give us the intensity. It might be a power relationship where we take the distance, raise it to some power, multiply by a number, and that equals the intensity. Or it might be an exponential relationship where we take a number and we raise it where the exponent is the variable, and then we multiply by a number and it gives us the intensity. Okay, so that's one thing we want to do, is find out which of those relationships is the correct one between distance and intensity. So this light sensor is on a cart, and there's a board here that's also on that cart. That cart can move forward and it can move back very smoothly and always point the light sensor right at the light bulb. Over here I have a sonic ranger that's going to be bouncing sound off of that board and coming back and measuring the distance that light sensor is from the bulb, also at 2/100ths of a second intervals. But I intentionally introduced error into these measurements. I intentionally left the sonic ranger a little bit behind the light bulb. So when the sonic ranger bounces sound and comes back and measures the distance, the actual distance that the light meter was from the light bulb was a little less. There was too much distance on every single measurement. And so that's where I want to introduce, let me come down here a little bit, two different types of errors. One is a random error, and random errors occur when you take measurements and some measurements are too high and some measurements are too low. It's like you're using a ruler that is not very precise. So you're kind of guessing it here, and sometimes you guessed high and sometimes you guessed low. And you can correct for random errors by having lots and lots of data. Many data points will average out the error. If some are high in data points and some are low data points, they will average out to be kind of at the correct level. That'd be a random error. A systematic error says maybe we had a much more precise ruler here, but as we were measuring the distances, we didn't notice that there was a rock between the ruler and the wall or something, so that the ruler was pushed off to the right, and every distance we measured was too short. But every distance we measured had the same amount of error in it, a little bit too short. And that's called a systematic error. So random error and systematic error. So let's come back over here. We'll zoom in a smidge. This column here is what the sonic ranger measured, and this column here is what the light meter measured. And the graphs here, I tried to pull the cart at a fairly constant speed, greater and greater and greater distances with time on the x-axis, distance here. So that's the calculations the sonic ranger measured for distance. The intensity over the same interval of time dropped off very differently. But one thing we can see, that as these numbers get bigger and bigger and bigger, greater distances, the intensity gets less and less and less and less. So it looks like they're inversely related right there. What we're going to do is we don't know what that extra distance is. We don't know if the distance is from here to the surface of that bulb or somewhere in the middle, but we do know the sonic ranger is well past where it should be. So I'm going to make an initial guess at what we should be subtracting from everything, and I'm going to say 0.05 meters. About 5 centimeters was what I'm going to initially guess at. The cell turned light green, and this time I have two different shades of green. A light green means we're on the right track, that my formula is correct, but it will turn a dark green when we actually get the correct value. So every one of those distances should have subtracted some amount, and I'm initially guessing that it was this amount. So I'm going to write a formula. It's going to be this number minus this number. But as I copy that formula down, I do want these cells to change, but I always want it to look over there at I-28, so I could put a dollar sign in front of the 28. I don't want it to change to row 29 or row 30 as I copy down. And it turned light green. So let's copy that formula all the way down here, and it is a long ways. We're collecting lots and lots of data points, but let me too far right there. Okay. So what we first want to do is check to see if the relationship between distance and intensity is linear. So I'm going to graph distance and intensity and see if I get a straight line. So I do want to use my corrected distance and intensity. So I'm going to copy that all the way down here, and I'm going to throw all those numbers into a chart. We're going to insert a chart, and it tried to guess what I was trying to do. It thought we were doing a column, but I'm going to do a scatter plot, a scatter. And wow, it sure looks like there is a relationship. I've got like 700 data points where this was the distance and this was the intensity. There is a relationship, but clearly the relationship is not linear. So I'm going to go ahead and delete that chart. All right, and I'm going to come up to the top here, and I'm going to remind ourselves what we had to do for power. If I graph distance and intensity and it curves, it might be power, it might be exponential, they both curve. But if I graph the log of the distance and the log of the intensity, if I get a straight line, then it follows this form. So what I need to do here is to come over and create this workspace here, where this is going to be the log of the distance and the log of the intensity here. All right. So I'm going to take the log of each one of these numbers. I say equals log open parentheses, and I want to use my corrected distance. Okay. So this number here is the log of that number there. If I take 10 raised to that number, it will equal that number. Copy that formula to the right. Now this is the log of this one, and this is a dark green because that number is correct. That number is not going to change. This number is going to change as we guess at the different extra distances we should have done. But I'm going to copy all those down, both those formulas all the way down to here. They're still highlighted, so I'm going to insert them into a chart. All right, it guessed we should do a line chart. They guessed wrong again, so we're going to come down here to a scatter. And it did something funny. what we have to do is click this box here, use E as my labels. So column E was our log of our corrected distance. And boy, that looks like a nice straight line. So it really does look like, because we got a straight line with log of distance and log of intensity, that tells us that it is a power relationship. I'm going to go ahead and just delete that, come back to the top, because we know now that it is a power relationship. It takes on this form. Okay, but knowing that it takes on that form, I got to find out what A is. A is going to be 10 to the intercept, and B is going to be equal to the slope. All right, so I'm going to type in equals 10 raised to the intercept of, and this is going to be a little tedious. I have to type in all the y values first. Okay, all the y values first, bringing them all the way down here. Okay, I'm going to hit comma, and then I'm going to put in all the x values next. And it's going to come all the way up like this. And let's see if right there. Okay, I hit enter, and that is the value of A. It was the 10 raised to the intercept, and those are the numbers that we plugged into the function called intercept to find out what that was. Okay, I'm going to take a little shortcut here. It's going to be the same numbers we got to plug into the next problem. So I'm just going to hit Control C, and then B was going to equal the slope. So I'm going to say equals slope of, and I'll hit Control V just to paste those same numbers in. All right, so I got negative 1.9354 for the value of B right there. Now, if we thought about this, X was our distance, Y was our intensity. If I used a different brightness of bulb for the same distances, I would get a bigger intensity. And that a brighter bulb would change the value of this. It would make it a bigger number. But it wouldn't matter if I had a brighter bulb or not. This number here would still be around -2. And I know that that number should be -2. I will talk about that in the next video, about why -2. So now that we're close, in fact, let me go ahead and calculate our percent errors of differences to see how close we are. So we're going to say equals, it's the absolute value, so I hit ABS for absolute value, open parentheses 2 times. It's the accepted value minus the obtained value. I close parentheses so that it can go ahead and subtract that. And then we're going to divide by the accepted. It's accepted minus obtained divided by accepted. And then I'm going to close parentheses. Okay, and 4.75% is what we got there. This was a formula that referred to those two cells. If I just copy that formula down one, it will use the numbers down one. Now we got 3.21% error, which is not bad, but that's because we just made our initial guess. If we didn't subtract anything from that, then our percent errors would have gotten bigger. See how each of these numbers here are the same as each number there. We didn't subtract anything. And the really neat thing is that these corrected distance cells here referred back to here, and the logs referred back to there. So changing this number is going to change this number, which are going to change those numbers, and those also referred to these numbers, so those would change. And these changed because they referred to those as well. Okay, so we thought maybe 0.05, I typed that in the wrong spot. We thought 0.05 might be good, and it got the number close to -2, but let's maybe guess 0.04, and that number is getting even closer to -2. Our percent error went down even more. Maybe it was 0.03. Oh, 0.03, like 3 centimeters subtracted from there, got us really close to there. And I think if you played with it long enough, you could really hone in on the right answer. I know that the right answer is 0.02885. Okay, and now the cells turn dark green because we really got our percent error almost zero there. But how would you play with that? By going up and down and seeing if it got closer or further. After a long enough period of time, you could play with that number and get this number right where it needs to be. But that was our systematic error. That was the extra distance we should have measured. We should have taken almost 3 centimeters off of every measurement. I do want to show you a really neat add-on for Google Sheets. It does sometimes work, but if you use Microsoft Excel, of course it would always work. But this is an add-on, and I've already put it in here. If you didn't have Goal Seek, you'd have to get the add-on and search for Goal Seek. But let me show you what this does. So we have these 3 things we have to fill out. Set cell to value by changing. What I want to do is I want to take this cell here, I'm going to select it, and then I have to hit here and it's going to put that cell into here. That's on sheet 1, cell H33. I want to set that cell to -2 by changing this cell. So I'm going to click on that cell and then click here to put it in what I've clicked on there. Now I have played with this a number of times today and I don't think it's working. We'll try it one more time, but it's thinking, and yeah, it screwed up. This is, I like Google Sheets for a lot of things, but it frustrates me to no end about this one. So we will undo that and go back to our 0.02885 there, and everything's good. Okay, now I want to talk briefly about what our results actually accomplish. We found that A was 0.04718 and B was really darn close to -2 when they're in this form. So the intensity was equal to that number times R raised to that number there. This number would change depending on the brightness of the bulb, but regardless, that number would be the same. So if I just leave off that number because it was specific to the bulb we were using, we could say that the intensity is proportional to radius raised to the power of -2. And I think this is an algebra 2 idea, but that is the same thing as 1 over the radius to a +2. And what that means is that the intensity is proportional to the inverse square of the distance. That's 1 over the distance squared. And that was the name of our activity in the spreadsheet. So now that we've looked at it mathematically and experimentally, let's just see if we can understand why that is the case more conceptually. If I had a piece of paper here in a dark room and that light is falling onto that piece of paper, no surprise, the further the paper gets away, the dimmer it gets, and the closer it gets, the brighter it gets. That's because the light is shining out into the room and the light is spreading out as it goes. So let's only look at the light that hits the 4 corners of that piece of paper and all the light that falls in between on that piece of paper. So right now, there is a certain quantity of light falling onto that area. If I were to take that piece of paper and go twice the distance, going twice as far that way would get twice the dimension here and twice the dimension here. Doubling the distance makes the area become 4 times as much. So whatever light was hitting the area here, that same amount of light is now spread out over 4 times the area. And the intensity on one little area is going to be 1/4 as much. If we go 3 times the distance, this becomes 3 times as much, this becomes 3 times as much, but the area becomes 9 times as much. So the light that was falling on one little area that amount of light has now spread out over 9 times the area, so the intensity on one little area is 1/9 as much. Same thing here, 4 times as much and 4 times as much. The area is 16 times as much, so the intensity would be 1/16 as much. As we are at these different distances, the intensity would be 1 over that squared. And that's because going twice the distance doubled this and it doubled that. So it's like doubling it squared. Twice as far, 1/4 the intensity. 3 times as far, 1/9 the intensity. 4 times as far, 1/16 the intensity. And you can just go out. If you were 9 times as far, the intensity would be 1 over 9 squared, or 1 over 81. So if I had a light bulb some distance from this table here, and I move that light bulb to twice the distance, so now we're at 2 radiuses away. No surprise it would be less bright, but how much less? Well, you double that and square it, that's going to be 1/4 as much. And then if we come up here to 3 times that original distance, 3 times the original distance squared, the intensity would be 1/9 as much. So if I had a light bulb here, a 60-watt light bulb, and I like the intensity of that bulb, but I just don't like it at that distance, if I wanted to move it twice as far, I would need 4 times as many bulbs to get the same intensity as one bulb at that distance. Or if I moved it 3 times as far, I would need 9 times as many bulbs to keep it the same intensity. All right, that's a little bit about how light diminishes with distance, but guess what? Gravity behaves the same way. Right now, it's maybe not even like, but it's an analogy at least, that gravity shines out into the universe and gets weaker and weaker and weaker with distance, similarly to how light does. The actual process is a lot different, but a way of predicting how much the intensity would be is the same. So if I had some amount of gravity here at Earth's surface, how much gravity would I have twice as far? Well, I'd have 1/4 as much gravity. And, excuse me, 3 times the distance, I would have 1/9 as much gravity, and 4 times the distance, I would have 1/16 as much gravity. It's kind of interesting that while we're standing here on Earth's surface, we are not 0 meters from the Earth. We're actually about 4,000 miles from Earth right now. Think about that for a second. We're about 4,000 miles from Earth. And that's because we measure the distance from the center of Earth's mass to the center of our mass, and the radius of the Earth is about 4,000 miles. So the farther and farther and farther we go, the weaker and weaker and weaker gravity becomes. So an astronaut going further and further and further away there, the weaker and weaker and weaker gravity becomes. So if I had an astronaut not drawn to scale, and they weigh 200 pounds right here on Earth's surface, if they were to climb the top of a very, very tall ladder, again, this is drawn to scale actually, but so that they went to the top of that ladder and they stood on a bathroom scale, what would they weigh there if the ladder is supporting their weight? Well, going twice the distance, the gravity would be 1/4 as much. Now, if the ladder disappeared and they became in free fall, the scale and the astronaut wouldn't be pressed into each other with any force, and you'd be, quote, weightless, even though you still had 50 pounds of force pulling you down. Just the scale wouldn't read anything. Now, this astronaut looks like they're a whole lot closer than 2 Earth radii away. In fact, let's say that this astronaut is at the same distance as the International Space Station. I said a moment ago that the radius of the Earth was about 4,000, so I'm getting a little more specific here. if they're at the distance of the International Space Station, it's about 254 miles above the Earth. So if this is the distance the astronaut is on the surface of the Earth, how far they are from the center, if they're this many miles above the surface, they're that many miles from Earth's center. I just added those two. So if you just take what fraction of the extra distance they are 1.064 Earth radii away. They're not 2 Earth radii, they're only about 1.06 Earth radii away. And so I can predict what their weight is because their weight is going to be proportional to the inverse square of that distance. And 200 over 1.064 squared is about 177 pounds of force on that astronaut. That's what they weigh. It looks like they are weightless, and they are in the sense that they wouldn't be able to press into a scale at all because the scale would have to be supported in place. We call this microgravity. It's not that they're truly weightless, they just wouldn't be squashed into a scale, but gravity's still pulling on them with a lot of force. So that's just an introduction to how gravity behaves as you get further and further and further from Earth.